Hello everyone, I'm Professor Xiaonan Gao. Welcome to the General Chemistry class. This session will continue with the basic concepts of chemical bonding. A chlorine atom shows a tendency to gain an electron as indicated by its electron affinity. From which atom, sodium or hydrogen, can the electron mostly readily to be extracted? Neither atom gives up an electron freely, but the energy required to extract an electron from sodium is much smaller than that from hydrogen. In Chapter 9, we learned that the lower its ionization energy, the more metallic an element is. Sodium is much more metallic than hydrogen. In fact, hydrogen is considered to be a nonmetal. A hydrogen atom in the gaseous state does not give up an electron to another nonmetal atom. Bonding between a hydrogen atom and a chlorine atom involves the sharing of electrons, which leads to a covalent bond. A covalent bond is a chemical bond in which two or more electrons are shared by the two atoms. Why should two atoms share electrons? Let's take a look at the fluorine structure. The circle represents the outermost electron shells of the atoms. The number of the dots laying on or within each circle represents the effective number of electrons in each valence shell. Each fluorine on the left side has 7 dots. When sharing electrons, each fluorine has 8 dots, corresponding to the outer shell configuration of argon. Note that we counted the 2 electrons between the fluorine twice. These 2 electrons are shared by the fluorine atoms. This shared pair of electrons constitute the covalent bond. Here's a Lewis structure of the fluorine molecule. 2 shared atoms from single bond in between, and the lone pairs are arranged on the side. Therefore, since there's only one pair of shared electrons, the formation of single covalent bond is obtained. The formation of water. 2 hydrogens shares their electrons with oxygen, and the Lewis structure of water is this way. 2 single covalent bonds between oxygen and hydrogen. Here, pay attention to the Lewis structure for hydrogen. That suggests these molecules, 2 hydrogen and 1 oxygen, have a linear shape. But actually, they don't. Lewis structures by itself does not address the question of the molecule shape. In the preceding description of the Lewis model for covalent chemical bonding, we have used a single pair of electrons between 2 atoms to describe a single covalent bond. Often, however, more than one pair of electrons must be shared in an atom is to attain a noble gas electron configuration. Carbon dioxide and nitrogen are 2 molecules in which atoms share more than one pair of electrons. First, let's apply the idea to carbon dioxide. From the Lewis symbols, we say that the carbon atoms can share a valence electron with each oxygen atom, thus forming 2 carbon-oxygen single bonds. This leaves the carbon atom and both oxygen atoms still shy of an octet. The problem is solved by shifting the unpaired electrons into a region of the bond, as indicated by the arrow. The bonded atoms here are sent to share 2 pairs of electrons between them, and double bonds form. Now let's try, on the other hand, at writing a Lewis structure for the nitrogen molecules. The sharing of 3 pairs of electrons exists between the nitrogen atoms. The bond between the nitrogen atoms then is a triple covalent bond. The triple covalent bond in nitrogen is a very strong bond that is difficult to break in a chemical reaction. The unusual strength of this bond makes nitrogen gas quite inert. As a result, nitrogen coexists with oxygen in the atmosphere and forms oxide of nitrogen only in trace amount of high temperatures. The lack of reactivity of nitrogen with oxygen is an essential condition for life on Earth. The inertness of nitrogen also makes it difficult to synthesize nitrogen compounds. So double and triple covalent bonds are known as multiple covalent bonds. As introduced previously, half of the bond length of a single bond of two similar atoms is called covalent radius. Like hydrogen, the distance between the two nuclei is 74 picometers, so that the covalent radius for hydrogen is 37 picometers. Therefore, a single bond length is usually the sum of two covalent radius of two atoms. Let's say a table of average bond lengths of some common single, double, and triple bonds. Take the carbon-carbon single bond, double bond, and triple bond for example. The bond length decreases, and this is a general trend for the bond length, which decreases from single bond to double bond, then to triple bond. It's not hard to understand. With the increasing number of sharing electrons, the two atoms usually get closer, thereby the bond length shortened. Alright everyone, in this class we learned the properties of covalent bond. I hope you have enjoyed the class, and I'll see you next time.